Howdy, howdy, folks. All right, good to see you all again. Today we are dealing with combinations of functions. So on combinations of functions, you can do a few different things. And so if you look here with me, let's see here, there we are. We can add and subtract them. We can multiply them. So a lot of times you'll see this like f of x times g of x, or you can divide them. So what we're going to do is we're just going to take two different functions here that we're dealing with, and we're going to combine them. So our first function is f of x equals 3x minus 1, and our second function is g of x equals 2x plus 5. So we're going to take these two functions, and we're essentially going to go through and combine them in every way, shape, and form that we know how. So let's try that here. First thing, I'm going to begin by adding. So for adding them, all I'm really doing here is I'm just taking f of x, and I'm adding the g of x function to them. That's what f plus g of x is. Now, you can use this notation where the f and the g are in parentheses. My own preference is I like to separate them, but it doesn't really matter. It's whatever works for you. So we have our f of x function, and we're going to add our g of x function. And all we're doing here is we're just figuring out what happens when we combine like terms. So ultimately we end up with 5x minus 4. 5x plus 4. So there's our f of g of x. And the same thing is we can also do this for subtracting functions. So 3x minus 1 minus 2x plus 5. Now, just remember, and again, you guys are pre-calc kids, so you've done this before. Just make sure you take that negative and you distribute it not just to the 2x, but to the 5. So we have 3x minus 2x, which is x, and negative 1 minus positive 5, which is negative 6. All right. So we end up with, oops. We end up with our functions. Now, if we keep going here, what happens when we multiply them? So f of x times g of x. So we're going to multiply the two together. So we're going to start off, we have our 3x minus 1. And we have our 2x plus 5. And again, if you want to foil it. You can multiply this any way you want to, doesn't really matter. Since most of you guys did generic rectangles in integrated math, that's what I'm going to do. So we are just going to go through and multiply this all together. And we'll deal with the domains here shortly on these. So we have our 3x. We have our negative 1. We have our 2x. And we have our plus 5. And we're just going to go through and multiply these really quickly. So we have 6x squared minus 2x plus 15x and minus 5. So when we combine our like terms, then we end up with 6x squared. Whoopsies, got to change colors back. 6x squared, positive 13x. and -5. Last and certainly least, we have f of x divided by g of x. So we take our two functions and we just put them over the top of each other. So 3x minus 1 over 2x plus 5. So from here, if they top and bottom factor out, or we can cancel anything out, we will, but it doesn't here, so we're okay. Now, the last part we're supposed to be doing here is we're supposed to find the domain for each function. So before you go through and try to figure out the domain, the first thing you had to do is figure out what the domains were for the original two functions. So the original function, f of x equals 3x minus 1, we're going to go back to what we did a couple days ago. And we're looking at it going, all right, is there anything in the denominator, or do we have any square roots? In this case, we have no denominators, we have no square roots, so the domain here is all real numbers. And the reason why we're going back to the original two is before we deal with the domain of any of these new functions, if either of these first two functions had something to do with their domain, something special in their domain, we have to take that with us. We have to include that in the domain of all the new functions. So even if the new function has a different domain, we have to first start with whatever's true here. And in this case, both these have a domain of all real numbers. So that means we don't have to worry about any domain conditions as we go to our original functions, or these new functions of ours. So let's take a look at this first one. F of x plus g of x was equal to 5x plus 4. All right, so if that's our new function, does that have any denominators? No. Does it have any square roots? No. So the domain for this will be also all real numbers. F of x minus g of x equals x minus 6. Does y equals x minus 6 have a domain? Restrictions. No restrictions, so again, it's going to be all real numbers. F of x times g of x equals 6x squared plus 13x minus 5. That's parabola. Parabola, just like the two linear functions before it, has no restrictions, so all real numbers. Our new function here, when we divided them, it has a denominator. So this one will have a restriction for our domain. And on this one, remember, if there is a denominator, we said the restriction is that the denominator cannot be equal to 0. So 2x plus 5 cannot be equal to 0. So when we solve it, then x cannot be equal to -5. Oopsies. Halves. So there's our domain. So these are our first 4 ways that we can combine functions. We can add them, we can subtract them, we can multiply them, and we can divide them. We keep going here a little bit. We also can use them to do this f of g of x and g of f of x. And again, you guys did this back in integrated 3, but let's remember what this looks like here for f of g of x. What that means, and now first of all, there are different ways to write that. So let's just talk briefly about how we can write this. One way to write this is f, some people call it fog, f of g of x. Some people like to write it this way, where they put the functions in this O. You got to remember, this isn't the letter O. That is the operation of, which means composite. And some people like to write it this way. where they'll take the outside function and they put it in the inside function. This is actually the way that I prefer to do it. But it doesn't matter. All three of these say the exact same thing. The biggest thing to remember here is that that letter O is not the letter O. It is the symbol for of. So this says the function f of the function g of x. The function f of the function g of x, or f of g of x. In other words, what it says is you're going to take whatever function is first, the g function, whichever one is closest to the x, or whichever one is on the inside. And so here this is why I like it. It's a little easier to see that it's the inside function, g. And you're going to plug it in for x on the other function. So the first one they're asking us to do here is f of g of x. So f of g of x. So the first thing I recommend doing is you always want to take your f function, your outside function. So I'm going to take this outside function here. And I'm going to go ahead and write that outside function. So the outside function was 3x and minus 1. So now wherever I see x on the outside function, I'm going to erase it. And I'm going to plug in the other function. So in this case, I'm going to plug in the g of x function, which was 2x plus 5. 2x plus 5. Should have made that one just a tad bit bigger. All right, and then we can go ahead and simplify from there. So 6x, and this is called a composition. So just another way to combine functions. So that means f of g of x equals 6x plus 14. And again, it's just a linear function, so the domain is all real numbers. All right, why don't you guys go ahead and pause the video, and why don't you guys on your own figure out what g of f of x is. All right, hopefully you got a chance to do that. So g of f of x, this means I'm going to start with my g function on the outside. So 2, in place of the x, I'm just going to go and put parentheses, plus 5. So I start with my outside function, and then I'm going to take my inside function, the f function, and I'm going to plug that in for x on the g function, the outside function. So 3x minus 1. So we end up here then with g of f of x. And that would be 6x plus 3. And again, it's a linear function. And since the original 2 had a domain of all real numbers and a linear function has a domain of all real numbers, this domain is also all real numbers. So this one was pretty straightforward. I'm going to give you guys another example to try here, where here's the 2 functions I'm going to give you. First one is going to be, here we are, f of x equals x squared minus 4. and g of x let's make this one the square root of x minus 3. All right, team. I want you to go through and figure out what the function would be for all 5 of the functions we're going to have here. So f of x plus g of x, subtract the 2, multiply the 2, divide the 2. I'd like you to go through and figure them all out. All right, so we're going to try to figure out all these here. All right, so f of x plus g of x, so I have x squared minus 4 plus the square root of x minus 3. So combining them is pretty darn easy. There's nothing that I have to worry about because there's no like terms. The domain is the hard part. So the domain on the first one is all real numbers. Remember, we got to figure out what our original restrictions were because we're going to carry those with us. And the domain on the second one, okay, notice I have a radical on this one. So that means automatically I have a domain that I'm going to have to carry through to every single problem. So x minus 3 has to be greater than or equal to 0. That means my domain for every single problem is going to have to start off with x is greater than or equal to 3. Now, no matter what happens, I will always start there. Now, I may add to it. There may be other domains that I got to deal with, but it always has to have that domain. So as I'm looking at this, x squared minus 4, square root of x minus 3, the domain is all real numbers. The domain is x is greater than or equal to 3. Are there any other conditions that I would add to it? No, because it has the same radical here that I had over here. So that means this domain is also going to be x is greater than or equal to 3. F of x minus g of x. All right, so we same thing. Bring them all down. X squared minus 4 minus g of x. So we're looking at the whole thing here. There are no like terms that we can combine, and the domain, well, it's going to be the same thing. Is x is greater than or equal to 3 because we didn't add anything to either of our two original domains. X is greater than or equal to 3. F of x times g of x. X squared minus 4 times the radical square root of x minus 3. I could distribute this radical in there if I wanted to. No reason to do it. It's not going to change how this function looks per se. But we go back and look at our domain. I still am dealing with the same domain as the original restrictions. of x is greater than or equal to 3. So bringing that one back down. I start with that original domain before I get to anything else. All right, we bring it back here again, f of x divided by g of x. So f of x was x squared minus 4. All over the square root of x squared minus 3. So we're starting with that idea of x is greater than 3, but notice on this one, that radical is in the denominator. So while the original domain said that x squared minus 3 has to be greater than or equal to 0, greater than or equal to 0, we know that if there's a denominator, it can't be equal to 0. So I have to take that one away. I don't know why I made this square in there, though. That's weird. Oh, that was bad. Don't want to do that. We're going to backtrack here just a second. I got to get rid of a square. There you go. All right. Oopsies. That's a little better. All right. So our original domain was x minus 3 is greater than or equal to 0, but I can't have that equal sign there because my denominator here can't be equal to 0. So I'm going to, instead of being x minus 3 is greater than or equal to 0, this time it's just x minus 3 is greater than 0. So that'll be my domain. So my domain then is not x is greater than or equal to 3. My domain is just x is greater than 3. So that's our domain. Let's do a little fog and goff here for a second. Start with my f function, my outside function. So we have this x squared minus 4. And I plug in my x minus 3 in for the x. And when we solve this here, notice the square is going to take away that square root. So I'm left with, got to rewrite this again. I'm left with x minus 3 minus 4. In other words, x minus 7, because the square and the square root cancel each other out. Well, this is a linear function. And usually the linear function, its domain would be all real numbers. But remember what we said. They have to follow the original two domains. And so since our original domain here was x is greater than or equal to 3, I have to use that domain again. So even though this is a linear function, I don't get to use the domain of all real numbers. I have to use my domain that of my two original functions as my starting point, whichever one was most restrictive. And now we have our g of f of x function. So we're going to start off with the square root of something minus 3. And we're going to plug in the other function into it, x squared minus 4. All right, now, when we're looking at this one here, let's see here. That means my g of f of x function that would be the square root of x squared minus 7. So I'm starting off, now I still have that domain of x is greater than or equal to 3, but I have another domain I have to think about as well. So I have to think about this x squared minus 7 also has to be greater than 0. So if that's the case here, that means if I were to back to that a little bit. I get x minus root 7, x plus root 7. And my domain then is going to be x has to be less than or equal to negative root 7, or x has to be greater than or equal to root 7. So I did my quadratic inequality. And again, we did those back in, oh my goodness, we did those back in integrated 2, didn't we? And then I compare that with my original domain. So the original domain back at the very beginning, remember that original domain was x is greater than or equal to 3. So I'm going to use, I'm starting with this idea of x as being greater than or equal to 3. And do these add anything to it, or do they restrict it further? Actually, they don't. So my domain on this one, we did all that work really for nothing. It didn't really help us out much. So our domain here is still going to be x is greater than or equal to 3. Biggest takeaway is just remember when you go and you're finding your domains, start first with those original 2 domains. Everything has to follow after that. All righty, let's go ahead and clear that out of the way here, and let's move to some other things here. What if I ask you to do some combinations based off a graph? So f plus g of -1. So what that really is asking you then is what is f of -1 plus g of -1. So we just got to go get some y values. So I'm going to look here, f of -1, here's -1. There's that value. And I have g of -1, it's right here. So what I'm really being asked here then is f of -1 is 1. G of -1 is 3. So 1 plus 3, turns out that value is 4. All right, why don't you go ahead and pause the video and see if you can't do something similar with these last 3 and see what you come up with, and then we'll take a look at it together. All righty, friends, here we go. On this one, f of 1 minus g of 1. F of 1, now that's right here. G of 1, that's right here. So I'm asking you what is -1 minus 1? That would be -2. So now here we have f of 2, f of -2, excuse me, times g of -2. And if we plug those in here, f of -2, that would be right here. G of -2, that would be over here. I end up with 2 times 4. That would be 8. All right, and our last one. We have f of g of 3. So the first thing I'm going to start off with is I'm going to start off and figure out what g of 3 is. So g of 3, that would be, right here, that's the value -1. So what I'm looking for then is I'm going to take that g of 3 value. And I think these are kind of fun. We end up having to interpret some of these kind of things in calculus a lot. So it's good for us to kind of get an idea of how do we evaluate it in pre-cal. So f of -1, that's right here. And that value is 1. All righty. Getting pretty close to the end here. All right, just got one more thing to look at. Let's go take a look at it. You're building a fence in your backyard. Now, we're told here to go ahead and use a graphing calculator. I don't think we need a graphing calculator. I think we'll be okay with that one. But let's see if we can't at least draw ourselves a picture of what we're looking at here. So what we have here is we have a side of our house. And what we're doing here is we're trying to build some sort of a fence where we have 300 feet of fence. Now, this is a rectangle. I could call it length and width, base and height, but because we're doing some advanced algebra here, some algebra 2 actually. I'm going to go ahead and call it x since that's horizontal. I'm going to call it y since that is vertical. So if we want to be really technical, which we should be, we should go ahead and tell everybody what we're doing here. Let x equal the width and y equal the length. So we should never just use a variable just to use a variable. We should always define it. So that means if that's x and this is y, by the way, that means that this right here is also going to be x as well. So our perimeter, our 100 feet of fence, has to be these two x's and this y. So we could say then that 100 is equal to both the x's and the y. What we're trying to do here is we're trying to write an equation for the area of the year. So that means the area of the year you can enclose. I don't think that year is even the word I should be using here. Area of the fence, or the area of the pen, or something. I'm not really sure, or the rectangle. I'm not really sure why a year is there. Whatever. All right. So area of this rectangle is going to be x times y. And since we are in algebra, I'll be honest, I really like to try to only have as few variables as possible. And plus, it tells me here to get everything in terms of x. So if I were to go back to this original equation of 100 equals 2x plus y, I think 100 minus 2x equals y. And if I were to substitute that in there, friends, I believe we have ourselves an area function in terms of just x. Now, by the way, this is the same thing here as the function a particular quadratic, actually. This is the same thing as negative 2x squared plus 100x. Well, if this is a quadratic, that means this right here is a parabola. If this is a parabola, that means my x-intercepts are 0. And this x-intercept, if I were to set this equal to 0, I'd find out the other x-intercept would be 50. Now, on part A, they asked us just to figure out what the equation is in terms of x. So these would be the equation here, or the answer to part A, the equation in terms of x. But what I'm doing here now is I'm looking at this knowing that it's a parabola, and I can use that parabola to help me kind of figure out where my domain is. So I know that I have some sort of parabola. And I'm not going to go below the x-axis. There's no reason to, because that would be an area. That would be a negative value. So this would be my y value, or my area value. And this right here, this would be my x value. So I don't need to go below this, because there's no way in the world I'm going to have an area that is greater than or less than 0. Can't happen. So my x-intercepts are 0 to 50. That means my domain over here then is going to be 0 to 50. So I could write this as an inequality if I wanted to. Or if I really, really wanted to, I could also write it as in set builder notation. So use a bracket, 0 to 50. Bracket again. Reason bracket, because our area could be 0. That is a legit value. Be goofy, but it could work. So I'm going to come back and do the maximum area here in a second. But I do know something about my vertex of my parabola. My vertex of my parabola has to always be between my x-intercepts. So if I have 0 and 50 as my x-intercepts, that means my vertex has to be located when x is 25. So I'm going to jump down to part D since I don't have a graphing calculator here. And I can actually figure out what the dimensions are because I know this equation right here. So if I want to figure out what that height is, I'm going to plug in 25 in for x. Figure out what the length would be. So in other words, that would be 50. It's funny to me. It says yards down here. Oh no, the largest yard. Okay. All right. So that means our dimensions then would be 20 feet. $25 feet, sorry about that. By 50 feet. And if I wanted to figure out the maximum area, just multiply those two numbers together and we will have our maximum area. So 25 and 50. If we multiply them, we will have 1,250 feet squared. And again, we're going to use our graphing calculators to learn how to find min and maxes in the second chapter when we get to that. But until then, don't worry about it. So there we go. Maximum area. All righty, friends. That takes care of I think that was 1.5, right? So combinations and compositions. All right. Have a good night.